Thank you. So this pH is like the temperature scale of someone who's sick, right? It really helps you monitor a lot of different things. So it's important, but then you can also use pH to, if you're going to react two things, what's the pH when you're all done? And a common way to react two things that they do in industry is to titrate. And you did that in lab. You titrated, and you found to see if Equate was cheating on their aspirin tablets or not, to see if the weight percent was right. And, well, what was the pH when you were done doing that titration? That is the question of what we're going to try to answer over the next two class periods. The class period today is just to set things up. We're going to set things up, and then the following class period, we're actually going to go and calculate the pH at the end of a titration or a reaction, right? Okay. So here's our titration setup, right? We're going to have maybe like a base in here and a weak acid in here. And then you sit here and you keep adding the base, right, until all that acid's reacted up. At the molecular level, everything's gone. How do you know when to stop adding? Changes color. Except we're supposed to use a technical terminology. We stop adding when we reach the what point? The equivalence point. That's the technical jargon. Equivalence point is just the volume that you add in the burette. How do you get that number? Oh, it changes color, so I would stop adding. Then you take V final minus V initial on the burette. Whatever milliliters of titrant you get, that's your equivalence point. Right? It's the milliliters of stuff in the burette. Titrant is the technical word. Okay. Predicting the acidity at the equivalence point of an acid-base titration. So we're just going to not go quite that far, but we'll set things up. Monica, give me a monoprotic acid. Now let's ask you first what monoprotic is. What's monoprotic? It's one something. One what? One acidic proton. Like HCl is a monoprotic acid. There's only one acidic hydrogen. Okay. So, Jessica, please give me a monoprotic weak acid. HCl is a monoprotic strong acid. What would be an example of a monoprotic weak acid? Anything that's not strong. Anything in that table, too. Remember that table, all those weak acids, all those Kas? HF, she said. Okay. And a strong base, Lauren. Give me an example of a strong base. Strong base. Now, the base part is OH. There you go, NaOH. Anything that will dissolve completely with the hydroxide. Pretty much Li, sodium, or potassium OH. Now, you said which one? NaOH. Okay. Assume your chosen weak acid, HF, hydrofluoric acid, is titrated with NaOH. What conjugate base or acid is being produced as this titration progresses? So we've got a bunch of HF in the Erlenmeyer flask, a bunch of NaOH in the burette. We're adding it. What conjugate acid or base are we forming? Eric, what are we forming? I like this statement, though. It's something to remember. If you add a base, you get a base. If you add a base, you get a base. What base do you get? F minus. That's the conjugate base. Add an acid, you get an acid, right? Okay. Anyway, what is the conjugate base or acid that is present, Alyssa, when the equivalence point is finally reached? It's still F minus, except it's just all F minus now, right? There's no conjugate acid HF left. It's completely F minus. Okay? Would the solution, Vanessa, be acidic, basic, or neutral when the equivalence point is reached? Why basic? Add a base, get a base. The base that's present at the equivalence point is what? The F minus, and it's a base. It's got to be basic. Write the chemical equilibrium, Mari, that determines the pH of the solution at the equivalence point. What would you write? The answers are always a Ka or a Kb reaction every single time. What would you write? Now, if you say Ka, that means at the equivalence point, you have to have an acid. It all reacted up. We had the NaOH. We converted all the acid to F minus. It's got to be a Kb, right? So it's got to be a Kb reaction. Maria, how would you write that Kb reaction? The reaction. Oh, not HF. There's no HF. And you have to write Kb. The Kb reaction, right? You've got HF. This is your conjugates. F, there you go. F minus plus H2O gives you OH and its conjugate acid. Good. Okay, everybody with me so far? Okay. Summer, here's one of our first calculations. Predict the equivalence point if 55 mils of a 0.15 molar solution of the acid, that HF, right, is titrated with 0.21 molar NaOH. Now let's ask Summer this. What are the units of your answer? What are they after? What are the units? It's milliliters, right? Because the equivalence point is milliliters. So it's going to be milliliters. It's going to be the milliliters. Actually, it's going to be the milliliters of NaOH. Right? You could actually write some English in there if you want. Usually we don't do it. We just stop at milliliters, but okay. Where would you start in this? We got to convert something. We got to start somewhere. What's that? That's dilution. M1V1 equals M2V2 is dilution. Here we're converting 55 mils of 0.15 molar HF into question mark milliliters of NaOH. We got to do a lot of converting. Yeah, we're going to need to convert stuff into moles. We're going to need a mole bridge. So my question is, where do you start? Remember the units that will tell us what to do? We're going to do this canceling game. We could start with molarity. We could. We could start with really anywhere up here. But the problem is imagine if you start with, I don't know, let's start here. If you imagine this, don't write this down. But let's just say you start here. Because molarity is what over what? Moles over liters. So you'd have moles of NaOH over liters. Now you want stuff to cancel. How do you know it's supposed to be written this way? It might be written as liters over 0.21 molar NaOH to get the right answer. So it's not a safe bet. You only have a 50-50 shot of getting it right if you do there. There's a better way to start. Start with the 55 milliliters. You can't screw up. There's only one other way you can't screw up. You're after milliliters of NaOH. Do you see the unit volume of NaOH up here? It's actually inside here, right? So this is the other safe way to start. I like starting this way because that's how we've always done it. I'm just saying here's another safe way to start. Liters over 0.21 moles of NaOH. That's another safe way to start. Then it's got to convert the liters to milliliters and somehow get rid of this one. Okay? But I think it's easier just to start there. But I see two ways to start. This is always start this way because life is so much easier if you do it this way, I think. Ramiro, what would you do first? And getting this milliliters to milliliters. Seems like we're done, but we're not. It's the milliliters of the wrong stuff. Yeah, it's for the HF. Yeah, convert it to moles, but we got to get the mils into what first? Liters. So what's the ratio there? 1,000 milliliters in a liter. Okay. Then we keep going, Caroline. Now what? Because our milliliters are gone. Now what? The hint is the big L, because you know it has to cancel, but it's not much of a hint. The only choice you have, you're right, is this liters and moles thing. Because 0.15 big M is really 0.15 moles over liters. So liter, 0.15 moles. And if you just stop here, it's confusing. It really is. You really got to say moles of what? It's moles of HF. So don't get lazy. Write it all out. Yep. Yeah, I got to try not to. So, but now we're missing something. We called it a what bridge? Mole bridge. We need to know, because moles of HF has to be on the bottom. Moles of what has to be up on top? NaOH. Yeah? The 0.15 right here. That is this. It's 0.15. Because it's 0.15 moles of HF per liter. And that's written right on. All I did is I changed the big M to moles over liters. So stop me. Any other questions? Mari? Yeah, you could skip this first part and just write 0.055 liters. That would work. But you can't really skip this part. What's our ratio going to be? It's 1:1. It's always 1:1. All right? Because all of them are what type of acids? What protic? Monoprotic. So it's always 1:1. So we're fine. Two last steps, I guess. What would you do next? The 0.21 moles. Okay, now we're going to use, do you see it? Monica, do you see this? Now we're going to use this one. 0.21 moles of NaOH has to go on the bottom. And then the liters up on top. And then liters to milliliters, exactly. That's how we'll get our equivalence point. Okay? Someone didn't give me my calculator back. Okay. 55 divided by 1,000 times 0.15 divided by 0.21 times 1,000 again. Yeah, about 39.3 milliliters. Right? So AJ, where's the starting point for all this? With the 55 milliliters, with the volume. Because you're converting volume of one compound into the concentration of the other compound, but you don't know its volume. So you're starting with the volume. And the nice thing about it is you're not going to start with 1/55 milliliters. You just write 55 milliliters. You can't screw up with the... And then they let the units tell you exactly what to do. They have to work out. And here's a big one. Don't just write moles of the compound. whenever you have the concentration term, right, moles of NaOH over liters of solution, or liters of solution over moles of NaOH. That's a big one, right? And you get it. Okay, here's same type of question, but a little bit of a twist. Victoria, we've got 100 mils of 0.38 molar HCN. It's titrated with 0.5 molar NaOH. What conjugate acid or base is formed at the equivalence point? What would you say it is? It's a conjugate base. What's its formula going to be? Well, no, just CN, right? Well, technically with a negative, but you're not, all right. I guess you could lose a point. Okay, cyanide. I put it in brackets because what do the brackets mean? Concentration, which is what over what? Moles over liters. I think you should write that out. And what will be helpful is instead of just writing liters, if you can remember this, total liters. Because what's wrong with saying, here's my volume? It's only one of them. What's the other one? Here's a hint. What's the technical word for it? The equivalence volume, right? You also added this. So you're going to have less or more than 100 milliliters when you're all done. Which one? A lot more. You don't know. You probably added, look at the last question. We added 40 mils. So you could have doubled the volume almost. So we got to figure out the moles of the cyanide, and we got to figure out the total volume. Okay. Which one do you want to do first? AJ? What's that, Jasmine? What do you mean first one? Oh, they're titrating. Oh, okay. You mean how did we figure out this was cyanide? Okay. Good question. It's not going to be messing with him because he's the strong base. So he's not going to, all those strong systems, strong acids and strong bases, they don't do anything. Once they're all reacted, they're a neutral solution. So we don't care about him. We're going to totally disregard him. All we care about is the weak system. And this guy is always either going to be a weak acid or a weak base. That's the one we care about. Because he's the one who's going to control the pH. He has a conjugate acid or a conjugate base that actually can control the equilibrium. You can write a Ka or a Kb reaction. So good question. We don't care about the strong stuff. Right? So when you ask what's the conjugate acid or conjugate base, it goes by this one. It doesn't go by the strong part. Okay, AJ, what was your answer? You want to do which one first, top or bottom? He wants to do top. Okay, we got to get the moles of cyanide, Albert. Equals moles of cyanide. Oh, I see what he's saying. You see what he's doing? He's using, oh, that isn't how I was going to do it, but this works. You see what he's doing? He's getting the moles of HCN. How does that help? Because it's the same as the moles of CN minus. You could do a mole bridge thing, but all the HCN gets converted to CN. So if you figure out the moles of HCN, you know the moles of CN. That's a good way. I didn't think of that. Let's do it that way. Albert's a genius. 0.38 has to equal the moles all over the liters, which is 0.1. So that'd be, yeah, that would be 0.038. So the moles of HCN equals 0.038. So I don't need this whole big, I was going to do this big long, do you know what I was going to do? I was going to do the big long conversion, starting with what? The 100 milliliters. But Albert's way makes a lot more sense. Okay, but that equals 0.38. We're going to have to. Okay, so the moles of CN minus equals the moles of HCN, which is going to be 0.038. Okay, so that we can stick right up on top. We've got that part. Okay, now we got to get the total liters. This number is going to be what plus what? Yeah, which liters? What number? The HCN liters, the 100 milliliters. Well, I can convert it to liters right away. It'd be the 0.1 liters. So we're going to have 0.1 liters, and that number is just coming from right here. But then you got to find, what is it called? Equivalence point plus the equivalence point. So we got to find the equivalence point. Start off with the 0.1. Yeah, you could skip that whole part about doing the milliliters thing. Right? You're right. You can start with the 0.1 liters times, what would it be? Jasmine, what would it be? It was 100 milliliters or 0.1 liters of what solution? Of that HCN stuff. And that's the only way to get rid of those liters. Okay. And then what would you do next, Monica? Yeah, the mole bridge. Yeah, good. Keep going. Perfect. Times. Now what? Jessica, now what? .5 moles of NaOH and liter on the bottom. Oh no, sorry, it's the other way around, isn't it? Otherwise my moles of NaOH won't cancel. And we could stop at liters, because isn't that what we want? Yeah, let's not go to milliliters. What do we get here? .1 times 0.38 divided by 0.5, about 0.076. So that number, put it in right there. So we can get, let's do what, red, our concentration of our cyanide. It would be 0.038 moles all over 0.1 plus 0.076 liters. All right? .038 divided by 0.176. About 0.216 or so, 0.2, somewhere around there. Yeah, and I get it. Or you could write moles over liters. Either one works. Big M is kind of quicker. Okay. So what we did is to get the concentration of the conjugate acid or base, first we just wrote an expression. Concentration is the moles over liters. And we got the moles part by setting up the big M equation using this mess. right? That's what we did right here. We got the moles, and then we had to get the total liters, so we had to add this volume plus our equivalence volume, and then we got it. Okay. You notice also that if you stopped right here, you'd have moles of HCN, right? That's another way of getting the moles of CN minus, is doing the exact same thing, but just stopping right there. Okay. Write the chemical equilibrium occurring at the equivalence point that controls the pH. So, Lauren, what chemical equilibrium can we write that's controlling the pH at the equivalence point? Yeah, it's going to be the Ka or Kb reaction. It's going to be a K. Oh, you said Cn. Cn's a conjugate base. So it has to be C. Okay. So how would you write that Kb reaction? Cn negative. Perfect. Uh-huh. And it's conjugate acid. Good. Okay. Find Ka or Kb for that equilibrium. Okay. Eric, you have your hand out because we're going to need the what to get it. Yeah, but Kb's not the Ka, yeah. So what is the Ka for this system? Exactly. Has to be for HCN. 4.9 times 10 to the negative 10. That's how we're going to get our Kb. Thank you, sir. Divided by about 2 times 10 to the negative 5. Okay. Extra question. Will the solution be acidic, neutral, or basic at the equivalence point? Everybody's going to be basic. Okay. Okay, so before we jump on this next one, I want to show you the homework for Friday. It's homework number 1, this sheet, and it's homework number 2, this sheet. And the numerical answers are there. So see if you can get them. Let's try this. 250 mils of 0.15 molar ammonia is titrated with 0.45 molar hydrochloric acid. What conjugate acid or base is formed at the equivalence point? And what is the concentration at the equivalence point? So go ahead, see if you can get it. See if you can figure this out. And I'll be glad to help you. Take a look at your neighbors. Maybe they can figure it out. Or they can explain it. So are you having trouble identifying what the conjugate acid or base is? Is anyone having trouble with that? It's got to be a conjugate which one? It's got to be a conjugate acid. Because if you're adding an acid, you're going to get an acid, right? So you need to write the conjugate acid. That means he must be a base, right? So you need to write the conjugate acid of that ammonia. And that is what you're hunting for. You're hunting for that conjugate acid concentration. So it would be what formula? Not of NH3, of NH4. Technically NH4 plus. This is what you're really after. Moles over the total volume. Yeah, so there's the moles. You got the top part. This concentration is moles over total volume. So you just got the top part. You're halfway there. Right? This is how you got the moles. Good. Then you got to, might help you to write equals moles over total volume. And that kind of guides you. Concentration equals moles over total volume. And you just got the top part. You figured out the moles part. Then this has to go in to get that total volume. Oh, nice. It should work, right? Looks good. Well, here, yeah, NH4 plus, its moles is going to be the same as this guy's moles. So I set up big M equals moles over liters, so 0.15 has to equal moles all over those liters. And then I'll get the moles of NH3, which is the same as moles of NH4 plus. So now you started here. Now you have to go all, now here you're getting an equivalence point. So that gets added into the bottom. Yeah. But this number, how'd you get the 0.1? No, you have to calculate it. You have to calculate it. It's not this.
Why didn't we calculate it?
We did. We did. Right here. We said that 0.38 has to equal x all over 0.1, and you get 0.038. So the moles is 0.038.
Okay. I guess I got confused.
No, it's not.
I mean, it's not, but
And it's not the same. But it's not the same. What'd you get for your liters? 0.083? Okay, everyone's getting that. Good. What'd you get? 0.113? So did you get 0.113 for A? Yes. Excellent. So did you end up writing a Ka or a Kb reaction for B? Ka, because you just formed a conjugate acid. Yeah. And then you need a Ka. I think this is the unusual case where you actually have to calculate it. Usually we can look up Kas. But for this one, you have to calculate it, don't you? Yeah. Ka is Kw over Kb. So you have to look up Kb for ammonia. 1 point what? Negative 5. All right, so you can get it. And you got 5.5. Okay, is that it? Yeah. See, so I think you're ready. Give the questions a problem. Give the questions an attempt. Come by if you need some help. I'll be glad to help you.